So I am writing another example which is given 2009. One of the roots of the equation x cube is equal to j, where j is equal to square root of -1, comma, is a, j b root 3 by 2 plus j times 1 by 2 c root 3 by 2 minus j times 1 by 2 d minus root 3 by 2 minus j times 1 by 2. Just I am going to give the hint. Answer is option B. Hint: x cube is equal to j. So this is your given complex number z is equal to x plus jy, okay, which is in the form of r into cos theta plus I sin theta. Instead of I, it is given j. Using that, you later check r value, theta value correct or not. That is, look at the previous problem procedure, you will get it. Cos pi by 2 plus j sin pi by 2. Okay, this is adding to k pi plus j times sin of pi by 2 plus 2k pi. Okay, so which implies x is equal to j to the power 1 by 3. That means the problem tells that cube roots of the given complex number j. The previous problem tells that square roots of minus I. Here I is nothing but j. Or you better to denote this small x by capital X, because small x is given in this notation, equation form. Okay, cos pi by 6 plus 2k pi by 3 plus j times sin pi by 6 plus 2k pi by 3, where k is equal to 0, 1, 2, because cube roots. Here 2 is nothing but n minus 1, last value. Next definition is complex function. Let A and B be two sets of complex numbers if every element of the form z is equal to x plus iy in A is associated with every element of the form W is equal to U plus IV in B, comma, then W is called a complex function of Z, comma, denoted by W is equal to f of Z. This W is nothing but U plus IV, Z is nothing but X plus IY. So it is a function, complex function from domain having a set A, all elements in the form of complex number Z is equal to X plus IY, codomain B, set of all complex numbers denoted by W is equal to U plus IV. So every element in the domain is mapped to a unique element in the second set. Then that mappings, that assignments, that associations is called a function from A to B. Okay, here that is complex function. Not every element is associated with a unique element. Just recall the definition of a function from A to B. A is domain, B is codomain. Every element in the domain A is mapped to a unique element in the codomain B. Then this is called function from A to B. Here that function is complex function denoted by W is equal to f of Z, where W containing two variables UV, Z containing two variables XY. Here two planes, W plane and Z plane. Z plane is the plane formed by real axis X axis and imaginary axis Y. And W plane is another organ plane, complex plane formed by U axis, U real axis, V is imaginary axis. Next, analytic function. A complex valued function. Just you can write here similarly in polar coordinates, comma, W is equal to f of r into e power I theta. W is nothing but U plus IV. Here you can add this one. U comma V are functions of X and Y. Here U comma V are functions of r and theta, expressing in Cartesian coordinates xy and polar coordinates like this. A complex valued function W is equal to f of Z is said to be analytic at a point Z0 if f of Z is differentiable at Z0 and in some neighborhood first you copy down this one. See, f of z is not only differentiable at z0 but also at every point of some neighborhood of z0. Neighborhood of a complex number tells that or gives that it is a set of all points z where mod z minus z0 less than delta. Delta is called the radius of that circle. That means it is the neighborhood of a z0 is nothing but it is the set of all points inside a circle with center at z0 and radius some r or delta. Okay. So taking z0, a point z0 as a center, we can draw, or there are so many circles formed with this center z0 in some circle. Inside that circle, at every point, the function should be differentiable. That is, at every point inside a circle with center at z0 and radius some delta. So neighborhood of a complex number z0 is nothing but it is the set of all points lying inside a circle having center at z0 and radius delta. Or you can write here some radius delta, because center is same. There are so many circles with the same center, that is called concentric circles. Radius only varying, radius only different. What is the concentric circles? Having same center but different radii. So you find some circle having center z0 and radius delta. At every point inside that circle, the function should be differential. Then only we say that the function is analytic at a point z0. And z0 is called analytic point of f of z whenever this definition is satisfied. f of z or if f dash z is exists at every point in a region which is also called domain or domain region or domain D, like that, then we say that the complex valued function W is equal to f of z is analytic in the region R. So the previous definition tells that analytic at a point. Now this definition this point tells that analytic in a region R. That means at every point f dash z exists. Not required to write here is if f dash z exists at every point in a region R, then we say that the complex valued function is analytic in the region R. See here, there is a difference, small difference between analytic at a point, analytic in a region R. Analytic in a region means in a region at every point derivative exists, f dash z exists. Then we can say we say that analytic in a region R. Analytic at a point, don't worry, the function should be defined at that point. That is for time being, for problem purpose, you understand like that. Okay. Now, not only at z0 f of z is differentiable, but also at every point in some neighborhood of z0. What is some neighborhood of z0? There exists a circle, that is at every point inside a circle with a center at z0 and a radius some delta. Okay, that means with a single point taking as a center, there are so many circles formed that all circles are called concentric circles having different radius. You find some circle with a center at z0 and a radius say delta. Inside that circle, at every point, f dash z exists. That is, f of z is differentiable. That is called analytic at a point. Okay. So it is difficult to find inside at every point the derivative exists or not. There is an alternative procedure, alternative theorem, which is invented by Cauchy-Riemann. That is called Cauchy-Riemann equations. There is a theorem called necessary and sufficient condition to say analytic in a region R. Okay. Next definition is if f of z is differentiable at every point in the complex plane, that is entire complex numbers, complex plane, then f of z is called an entire function. Now what is again a small difference in this definition? Throughout the complex plane, at every complex number, f dash z exists. That is called f of z is differentiable at every point in the complex plane. Then such function is called entire function. The name itself is called entire. Such standard functions, what are that? sin z, everywhere differentiable. Cos z, everywhere differentiable. Okay, e power z, exponential z, everywhere differentiable. Polynomial function, everywhere differentiable. Constant function, everywhere differentiable function. Okay. Example, constant z power m, polynomial function sin z, cos z, e power z. Okay, so these functions everywhere differentiable in the entire complex numbers, that is entire complex plane. And analytic function is also called regular function or holomorphic function. Okay, the synonyms of analytic function is holomorphic or regular function. Next, the necessary and sufficient conditions for W is equal to f of z is equal to u plus iv to be analytic in a region capital R, in a region capital R, or that first condition. The four partial derivatives exist and are continuous on R sorry, here I forgot to write the four partial derivatives. Just I am writing dou u by dou x, partial derivative with respect to x of u, partial derivative with respect to y to u, partial derivative of v with respect to x, partial derivative of v with respect to y. These four partial derivatives exist and are continuous on R. And the second condition is dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So these equations are called Cauchy-Riemann equations. In bracket, simply CR equations. See, if the given complex valued function f of z is equal to u plus iv, or w is equal to f of z, or you can represent like that, three equal terms, to be analytic in a region R, is analytic in a region R, then these two conditions are satisfied. What is that? The four partial derivatives, dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y exist and are continuous in R. And the second condition given two equations which are called Cauchy-Riemann equations. Dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. If f of z is analytic, then these two conditions satisfied. To prove a function is analytic, you have to show these two conditions, then only we have to say, or we can say is analytic in a region R. Okay? See, in polar coordinates, comma, the CR equations are dou u by dou r is equal to 1 over r, dou v by dou theta, and dou v by dou r is equal to minus 1 over r, dou u by dou theta. Just by heart these two and the conditions in two CR equations in both systems. See one example. After that I will give the method to find f of z whenever u or v is given, or whenever u or v is given, how to find the other. For what values of a, b, c, d, four things you are going to find, comma, the function f of z is equal to x square plus axy plus by square plus I times x square plus dxy plus cy square is analytic. Solution. So here the function is given to be analytic. Now we need to find ABCD values. F of z is equal to x square plus axy plus by square plus I times x square plus dxy plus cy square, which is in the form of u plus iv, I multiplying term, that is the coefficient of I, that is multiplying by I, which is denoted by v. The term do not containing I, that is real part of f of z, u. Okay, is analytic. So whenever analytic, use the second condition, that is CR equations, Cauchy-Riemann equation. Therefore, CR equations are satisfied. What are CR equations in x comma y coordinates? Implies dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. So partial derivative of u with respect to x, which implies u with respect to x 2x plus this derivative, this term derivative ay, and this is going to 0, is equal to v with respect to y partiality, so x square 0, so dx with respect to y, cy square derivative 2cy, and on other side second equation u with respect to y partially, so axy derivative ax plus by square with respect to y 2by is equal to minus of v with respect to x partial derivative. So 2x plus dy. So equating like terms, which gives d is equal to 2, a is equal to 2c. On the other side, a is equal to minus 2, 2b is equal to minus d. So substitute this d value there, which gives b value, substitute a value here, which gives c value. So a is equal to minus 1 and 2b is equal to minus 2, b is equal to minus 1. Sorry, here c value gives. Substituting a is equal to minus 2 here, 2c is equal to minus 2, c is equal to minus 1. Substituting d value there, which gives b value is equal to minus 1. And these four partial derivatives are polynomials, which are every polynomial function which is always continuous. They exist as well as continuous. Note. First point. U is equal to real part of f of z and V is equal to imaginary part of f of z. Just like comparing with x and y, here in that order uv. Z x y, here f of z uv, like that. 2. If f of z is equal to u plus iv, that is, or you can write w. If w is equal to f of z is equal to u plus iv is analytic, then f dash z, the formula for finding f dash z, which is also dw by dz, is equal to dou u by dou x plus I dou v by dou x. So this is the basic formula for finding f dash z whenever f of z is analytic, because don't apply your one variable, x variable, real variable technique here directly. If a function is known to be analytic, then the formula for f dash z like that. It does not mean that finding f dash z, the procedure of f dash x, okay, because u is in terms of x and y, v is also sometimes in terms of x and y. Don't apply your one variable 11th standard derivative techniques. So first of all, you prove that function is analytic, then the formula for f dash z is the two terms u comma v, partial derivative with respect to x, dou u by dou x plus I times dou v by dou x. Some standard functions which are always entire functions, that is, which are always analytic. What are that? Exponential z, sin z, cos z. So their derivatives are nothing but, their integrations are nothing but what we have studied in real variable, x variable techniques, differentiation and integrations in 11th 12th standard. In such cases only you can apply directly f dash z and integrations whenever the standard functions are there. In all other functions you apply this method, finding derivative. Okay. And with the help of CR equations, I can write in other representations of f dash z. So dou u by dou x, keeping same, dou v by dou x using CR equation becomes minus I dou u by dou y. And the third representation of this, but basic, just remember this basic result. Okay. All other representations according to the options, 1 mark question, 2 marks questions, this point may comes. Instead of original value, original term, it is also obtained with the help of CR equations, many more representations that are useful in 1 mark, 2 mark questions, okay, according to the options. Dou u by dou x is nothing but dou v by dou y, and keeping that same term, plus I dou v by dou x. Another representation, last representation, dou v by here both are v, both are u, both are x, both are y, I didn't get. So dou v by dou y keeping same, and that is minus I dou u by dou y. In polar coordinates, comma, f dash z is equal to e power minus I theta into dou u by dou r plus I times dou v by dou r. If f of z is equal to u plus iv is analytic. Whenever this function is analytic in polar coordinates, the formula for finding f dash z, this one, e power minus I theta. Next, 3. A function f of x comma y satisfies the Laplace's equation, that is del square f, yesterday I had given del square notation, is equal to dou square f by dou x square plus dou square f by dou y square is equal to 0, comma, he is called a harmonic function. Fourth one, if f of z is equal to u plus iv is analytic, then its real and imaginary parts, that is u and v, satisfies Laplace's equation, that is u and v are harmonic. In this case, u is harmonic conjugate of v and vice versa. See, whenever a function is known to be analytic, its real and imaginary part, that is u comma v, satisfying the above Laplace equation. These proofs, note points, everything available in complex variables textbook, what you have studied in BTech first year or second year. Okay, just I have given that note points which are helpful for in 1 mark 2 marks questions only, because proofs are excluded. If you want to understand these things, proofs are available in the beginning of the first chapter of complex variables. Okay, next, so u is called conjugate of v is called conjugate of u, provided f of z is equal to u plus iv is analytic. Because the question asks, if u is given, how to find v? If v is given, how to find e? How to find u? Provided f of z is equal to u plus iv is analytic. That is going to discuss now. Okay. Remember the Cauchy-Riemann equations in both systems. Remember the formula for finding f dash z in both systems whenever f of z is analytic. Okay. And Laplace's equation, that is also 1 mark questions, these 1 or 2 marks questions. Now I am giving the procedure for finding u whenever v is given, finding v whenever u is given, and whenever one of these given, how to find f of z. Two methods are there. Now the problem starts after this discussion. You will get interest also. Okay. Construction of analytic function f of z or determination of conjugate function. Conjugate function means u is conjugate of v, v is conjugate of u. Two methods. Method 1 named as total derivative method. In each method, two cases, case 1 or case A. Let the real part u of an analytic function f of z is equal to u plus iv be given then how to find v, comma, we proceed as follows. Since v is a function of x and y, or you can write, let the real part, instead of u, you can write u of x comma y, because first of all I am going to derive this Cartesian coordinates, u of x comma y. Instead of v, write v of x comma y and then comma we proceed as follows. Therefore, what is total derivative definition in partial differentiation I have given? dv is equal to dou v by dou x dx plus dou v by dou y times dy, because it is a function of two variables. Because we don't know dou v by dou x, dou v by dou y, because v is going to find, so use your CR equation. That is the advantage of CR equations. What is CR equations here? Minus dou u by dou y into dx. Dou v by dou y is nothing but plus dou u by dou x into d. Let us say equation 1. Since by CR equations, and it looks like in the form of RHS of equation 1, if I denote this is m, denote by n, it is in the form of exact equation, differential equations, exact differential. Okay. Since RHS of equation 1 is exact, therefore integrating 1 we get, integrating this equation 1. Just you will understand this term in problems why it is exact. Okay, actually it is a proof. I will show you in the problems how the RHS is exact. we get left side after integrating derivative cancel, which gives simply v on the right side. Whenever an equation m into dx plus n into dy is exact, how I gave the solution procedure? Integral m dx, what is m? Minus dou u by dou y dx, this is denoted by m. In this we keep y constant, y terms constant. Look at the procedure of exact equations in first order differential equation ODE chapter. Plus in n terms do not containing x, terms not containing x, in n means what is there? Dou u by dou x, that is this is n. All these terms with respect to y and adding c. Just it is nothing but the procedure of solution of exact differential equation, first order differential equation, exact last exercise, okay, keeping y constant, all these things. That's why I denoted that method, these terms by that method, m into dx plus n into dy. So this is the procedure to find imaginary part v of x comma y whenever real part u of x comma y is given of the given analytic function f of z is equal to u plus iv. Just interchange, you will get case 2, case B. Don't worry, all the you can easily understand while we go for problems, whenever we enter into the problems. Case B. If v of x comma y is given of an analytic function f of z is equal to u plus iv, then to find u of x comma y, we proceed as follows, just like as above. Here we are going to find u, so you start with du formula, which I have given already in the case A dv, because both are functions of x and y. Since u is a function of x and y, therefore partial differentiation total derivative topic du is equal to dou u by dou x dx plus dou u by dou y into dy. We don't know these two values because we are going to find u. Use your CR equation, convert into v. Dou u by dou x is nothing but dou v by dou y into dx, and dou u by dou y is nothing but minus dou v by dou x into dy. Equation 1 using CR equations. It is in the form of, again RHS of equation 1 is in the form of m into dx plus n into dy. Integrating, I am not writing that sentence RHS of equation 1 is exact because I already explained, given in case B, A. We get integration derivative cancel u, and this is integral m dx, that is dou v by dou y dx. So this is m, keep y constant, keep y constant, which I have given, plus integral terms not containing x in n. What is n here? Minus dou v by dou x. This is your n. All terms with respect to y plus c. This is the procedure to find u whenever v is given. This is m into dx. Keep y constant. Just by heart that procedure. Not required to by heart. Just you need to remember CR equations. With the entire topic of first chapter completely depends on CR equations. Without CR equations we cannot find anything. So the CR equation plays an important role in this chapter. And the analytic, again, it is a basic definition which is useful in all the coming topics and definitions. Without analytic we cannot approach further.